is it not possible to have the same number of dots on the inside as on the boundary? So how many dots are there on the inside of this one? How many dots are there on the inside of this hexagon?
7.
Yeah. 1, 2, 3, 4, 5, 6, 7. Okay, someone stop doing that.
12. There's 12
Good.
on the outside.
Yes, that's correct. Okay. Now, is 7 equal to 12?
7.
Is it? No, it's not.
No.
So that means the number of dots on the inside is different to the number of dots on the outside.
So,
What if I drew a smaller hexagon like this one? How many dots are there on the inside?
1. So if we stretch it, there will be 3 more on the outside.
Mhm.
I mean, if we stretch it, there will be.
But we're not allowed to stretch it. We're not allowed to stretch it because the question said for a regular hexagon. The question's asking only about regular hexagons, and it says for a regular hexagon, how come we can never have the number of dots on the inside equal to the number of dots on the outside? That's what the question says.
Oh. Well, I know a reason for the one with only 1 dot inside. Because if you stretch it, you'll have in the inside there will be 1 more, but there will be there will be more dots on the outside.
True. So when you say stretch, do you mean make it bigger, like this size?
No, I mean like.
Okay.
The
question is.
I mean like this. So you stretch it like this.
Wait, what color are you drawing in?
Blue.
Oh.
Like you
stretch. Yeah, but is this hexagon regular?
Regular.
Yeah, is this a regular hexagon? Do you remember what regular means?
Yeah.
What does it mean?
Number of dots.
It means that, well, there has to be 6 sides for it to be a hexagon. But then what's the other thing that makes it a regular hexagon and not just a hexagon?
They have the same amount of dots in each side.
Yeah, exactly. Which means all the sides are equal in length. So is this one a regular one?
No, like what I mean stretched is like this.
Yeah, so this one's a stretched one, but we don't want to think about the stretched hexagons because the question asks us about regular hexagons. So let's not think about the stretched hexagons. Okay, so in this case, there are less dots on the inside than there are on the outside. So when the side length has 2 dots, when the side length has 2 dots, then the inside is 7 and the outside is 12. So that means that the inside has less dots than the outside. Does that make sense?
Yeah.
Okay, what about if there are, So what about if there's even more? I'm gonna draw more dots. Okay, so can people see in red? I'm gonna draw a 4-sided hexagon this time. That's a lot of sides. So 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and one, 2, 3, 4. And then how many dots are on the 4-sided hexagon, the pink one? Like how many dots are on the outside of the pink one? So do you remember how we were counting it? We were looking at, we first count 3 for one of the sides, but then since we already counted one of these dots.
Then we count 2.
Yeah.
2 until we get to the last dot.
Yeah.
And then we just, for the first one we counted, we just give a dot to the one we were about to count.
Exactly. So we take away from the 3, turn it into a 2, and then give that dot to the 1 to turn that into the 2. So, but why 2? 2 happens because we had to take 1 away from the side length of 3, right?
1, 2, 1, 2.
So when we did the 4 case, we started with 4 dots at the top, and then we had to take 1 away from 4.
2?
So we took 1 away from 4 to get 3.
1, 2, and then 1 here. So 2 here, 1 here, 1 here, 1 here, 1 here.
So 2 is equal to 3 minus 1. Do you agree?
Wait a minute. Why is it like this? Because at the end for 2, I'm pretty sure 3, 4, 5, 6, 7. Why 7?
Did you draw the 9 case?
No.
Okay.
Yeah, but yeah, I did.
Oh, you did?
Yeah.
Okay. But let's try to do it without even drawing it. That's the point here. I want to find out how to count the outside dots without drawing it.
You have to count. Wait a minute. If each side is 6.
There are 6 sides.
And then you have to do 9 on each side. You just do 9 plus 8. 9 plus 8. No, 8 plus 8. 8 times 6.
Wait, but remember when it gets to the last side, you have to do something special?
Yeah, you have to give 9 to the...
Oh, yeah. And then so instead of the 9, we make it an 8.
It's 48.
Yeah, so that's 8 times 6.
Yeah.
Which is 48. Okay, good. So you found the pattern. Can you tell me what the pattern is? Why did we do 8 times 6 when it was the 9 case?
Because we already know that on the last one, we need the first row we counted is 1 more than all the others. So we put that 1 to the 1, and then it will only have like 8 left. Yeah. And then since there are 8 sides, and then now we have 6 sides, and then and now all of them are equal to with 8. You just times 8 times 6.
Good. Okay. So then without drawing it, how do I know that the number that I want to times by 6 is going to be 8?
Yeah.
Well, you knew that because you know that you start by counting the 9, and you know that because you've already counted one of them, you take away 1 from 9 to get 8, right?
Yeah.
Okay, good. So in the 9 case, you do 9 minus 1 times 6. And in the 4 case, we do 4 minus 1 times 3, right?
Yeah.
And in the 3 case, we do 3 minus 1 times 6, right?
Yeah, that's 12.
Yeah, so we always look at the number of dots on one side, which is 3 in this case.
Yeah.
You subtract 1 and then you multiply that number by 6. That's how you do it, right?
Yeah.
Okay, so can you tell me, what if the side length was equal to 21?
21.
Yeah.
Then the side, okay, then just 6 times 20. No.
6 times what?
No.
6
thinking
times?
6 times 21. I was thinking that.
Not quite 21.
Wait a minute. 21 and all the 20 times, wait, what? 20 times 21.
20 times 21?
No.
No, we need 6 because we add up.
6 times 20.
6 times 20, yes. Good, because 20 is 1 less than 21. Because 21 minus 1 is 20. And it has to be 20 because you know you have to take away 1 dot before you add up that number 6 times. Okay, so that means if the side length is n dots each side, then my formula, which tells me how many outside dots there are, is n minus 1 times 6. Does that make sense? Because you just take 1 away from the side and then you add that up 6 times, right? Okay. Okay. So my next question is, how can we count the number of dots on the inside? How many dots inside? And again, I want to do this using some kind of formula so that no matter how big I make my hexagon, I can always have a way to count how many dots there are on the inside.
If you look at the example, if you look at the inside, it has 1 and then it turns into 3.
Okay, so you're saying that when we start with a smaller hexagon like this, it's 1.
Oh, okay.
So how about, I have a special way to do it. Do you know how many dots are here?
How many dots are where?
Can you see the screen?
Yeah, like in the 1?
Yes, there's 1. Okay, can you tell me how many dots are on this hexagon?
How many dots on which? 6?
Okay, but how about
1 on each side? Because there's 6 sides.
Yeah.
And then all together is 6.
Yeah, so
and then 1 times 6 is 6.
Good. Okay, what about this hexagon here?
That one.
Do you remember our formula? So how do we count it?
7 dots inside.
Wait, no, I mean on the outside. So how many dots are on the outside of this hexagon? Do you remember the formula we just talked about? So
yeah, 4, and then there's 3. So 3 times 6, 18.
Not 3, but remember we have to take 1 away.
Yeah, that's 2. But then we start with the 4. Oh,
so it's 2 times 6, right?
Yeah, 12.
Yeah, okay, so 2 times 6 equals 12. And this one was 1 times 6 equals 6. So then how many dots are on the inside altogether?
dots in the inside.
Yeah, all together.
Let's see.
So there's 12 on this hexagon, there's 6 on this hexagon, and there's 1 in the middle. So if I want to count how many dots are on the inside of this big pink hexagon, how do I get that?
How do you get?
Yeah, how many dots are on the inside of the big pink hexagon, the big pink one?
I mean,
Well, you just counted them in different sections.
oh yeah, 17.
Ah, so you, wait, it's not 17, it's 1 plus 6 plus 12, right?
Here was the silver. Yeah.
Yeah.
Oh.
Because it's
Oh,
the middle bit
Oh.
plus all the dots on this hexagon plus all the dots on this hexagon.
Oh, yeah.
Yeah, and we already counted that it was 12 for the bigger one, 6 for
That's
this.
19.
Yeah, 12, yeah, it is. It's 19. Okay, good. Okay, so what's the difference? It's like, oh, okay, what about this big pink hexagon? Can you tell me how many dots are on the outside of the big pink hexagon?
The big pink, pardon?
How many dots are on the outside of this big pink hexagon? The biggest one here.
The biggest one?
Yeah.
So that's
So-
3 times 6, 18.
Yeah, very good. 3 times 6, because you just take one less than the side
And
length.
then you just times it by 6.
Exactly. So 3 is 4 minus 1, and you times that by 6. Okay, I think.
What? So if you count your first like row of your dots on the top,
Mhm.
you see 5, right?
Yeah.
And then you just minus it by 1. That's
Good.
4. Because like the last one.
Mm-hmm.
Yeah.
Okay, so if it's n, instead of 5, put n there. You start with n dots on one of the sides, and you have to minus 1, right?
Yeah.
So that's why it's n minus 1. And then you multiply by 6. So in the 5 case, then we just put n equals to 5.
Yeah.
And we get 4 times 6, which is 24. Or if
So
n
you don't,
equal,
so it doesn't really need to tell you how much the sides equal, because you can just look at it.
yeah. But what if n is equal to 3? Then what does my formula give me?
In your formula inside, the inside is the same as, oh no, it can't be for regular. If it's 3, oh, it'll be 12.
Yeah, so because 3 minus 1 times 6 is 12.
2. 3 minus 1 equals 2 times 6 is 12. So
Yeah.
that's n.
So do you see how this n formula makes it like so that I can use whatever number I want instead of n? So that's why this n formula is useful.
So you don't need to actually write the real number.
Yeah, exactly. I don't have to write the actual number. This is just like a replacement. It's just like something to represent the real number that I put in there.
Yeah.
Okay, good. So that's how many dots there are on the outside. And then what did we do to count the number of dots on the inside?
Oh, you just. You did the same thing. You did the same thing, and once you get all your 3 or how many you have answers, like you just add all your answers together, and that's how many inside. And if you want to know how much altogether, do the same like technique, and then do the same technique, and then you add your answer with the 3 answers combined together, and
Yeah, that's exactly how we did it. So remember that, yeah, so you find all your hexagons on the inside and then you add everything up together. Okay, I'm gonna fix this hexagon thing that I drew incorrectly. So yeah, it was something like this. You did the outside one, and for the outside one, because here, what is n equal to in the outside hexagon?
Why
is the real value of n when I look at the outside hexagon?
The real value of n is 3.
Are you sure about that?
No, 4.
Yeah, 4, good. So that means that the number of dots is 4 minus 1 times 6, which is 18. Okay, and then what about here for this hexagon? What's n equal to? For the hexagon that I just drew inside it. Anyone? What's n equal to? What's the real value of n when I look at this inside hexagon? So just as a reminder, n is like what I write to represent the number of dots that are on one of the sides. So for the big hexagon, n represents the value 4.
Yeah.
And then for this hexagon, what does n represent? How many dots are on one side? Can anyone tell me how many dots are on one side?
Dots on one side?
Yeah.
4. Well, 3.
Wait, yeah, okay. So then what's the real value of n for this hexagon? Jaden? Can you tell me what n is for the smaller hexagon?
N equals to 3.
Okay, good, good, good. What about this one on the inside, the even smaller one?
N equals to 2.
Good. Okay, and then this is just 1 dot. Okay, so this has 1 dot. And then for the n equals 2 hexagon, I can just do my formula, n minus 1 times 6, which is 2 minus 1 times 6, which is 1 times 6, which is 6. And then for the n equals 3 hexagon, to count that, I just do 3 minus 1 times 6, which is 2 times 6, which is 12. So basically, what we have is outside, we have 4 minus 1 times 6. But on the inside, we have to add all these values up. So we start with our 1 dot, 1, plus, this was 1 times 6 for the next hexagon. 1 times 6, plus, for the next biggest hexagon, this one here, it was 2 times 6, 2 times 6. And then that was, yeah, so this is equal to 19, and this is equal to 18. And they're not the same. Okay, so if we want to talk about any sized hexagon, so for different values of n, so n dots on each side, then the outside has, like we did before, the same method, n minus 1 times 6. But then the inside, we basically have to add up all the different ones. So we have to add up the 1 first, and then we start from the next biggest hexagon, which always begins with 1 times 6. And then we have to go all the way up. So 2 would be for the next biggest hexagon. That's bigger than the 1 times 6 hexagon. And then we keep on going. We just make the hexagons bigger and bigger. And then we keep on adding things up until we reach the number that's just 1 less than this number. So the number that's 1 less than this number would represent the hexagon that's just inside. So the biggest hexagon that's inside our largest hexagon. So that would be n minus 2, because that's the one that's 1 less than this big hexagon. Okay. And then what we can do is we can combine these two. And the reason I want to combine them is because this has a minus 2. So if I subtract 2, but then I add 2, then it becomes 2 times 6 plus n minus 2 times 6, which is equal to n times 6. And then n times 6 is more than the outside number of hexagons already. So that already tells you that the inside has more than the outside.
Yeah.
But that's only, this is where we stop when n is equal to 3. No, it's not. This is where we stop when n is equal to 4.
What do you mean? This is where we stop.
So remember that when n is equal to 4, like this case here, the inside had 1 plus 1 times 6 plus 2 times 6. And we don't add any more. We just stop at 2 times 6. So we stop here for n equals 4.
Yeah, in general, you stop at n minus 2, right? So
we stop here when n is equal to 5. So we always stop when it's 2 less than the number n. So if n is bigger than 3, then what we can do is we take the 1 times 6. Because when n's bigger than 3, then the 1 times 6 is always there. And then we can add that to the last number. So we take the 1 times 6 and we add that to the last term, which is 2 times 6 when n is equal to 4. But it's 3 times 6 when n is equal to 5. So when n is just anything, you just take away 2 to find out where you stop. Okay. So if we add the 1 times 6 to the very last term, n minus 2 times 6, then what you get is 1 times 6 plus n times 6 minus 2 times 6. So if I just take this one, it's n times 6. And then I go 6 minus 2 times 6, which is 6 minus 12, which is minus 6. And then that becomes just n minus 1 times 6. And then that's equal to the outside. So that means if I just take my 1 times 6 and my very last term, I get what's on the outside. So this is equal to the outside term. But I know that my inside has more because I also have this 1. So if I also add the 1, there's at least the number of dots on the outside plus this 1. And so that proves to me that if n is bigger than 3, then my inside always has more dots than my outside. And we already checked when n is equal to 2 and n is equal to 1 somewhere. Where did we check it? So, okay, we checked n equals 3, which we need to do because this thing here, inside bigger than outside, was for n greater than 3. So when n was equal to 3, we saw that the inside was actually smaller than the outside, which is the opposite thing to what happens when n's bigger than 3. And then it's not too hard to check when n is equal to 2 because there's only 1 dot in the inside. So when n is 2, there's only 1 dot on the inside. So that means the inside and the outside aren't the same. And when n equals 1, it's just a dot. I don't even know if you would consider this a hexagon. So basically, we showed that for n equals 2, inside is not equal to outside. And for n equals 3, inside is smaller, so inside not the same as outside. And then for n equals 4 or bigger, so just anything that's bigger than 3, we found that the inside has more dots than the outside. So again, inside is not the same as outside number of dots. So we basically—
Yeah, so can you see that like people had like a simple idea, and if you can write it out precisely, it actually turns into a good explanation.
Yeah. So we basically checked all the possible types of regular hexagons because it's not enough to just show it for one type of regular hexagon. Like you can't just show it for this size hexagon. You have to show that it's true for every size hexagon. And we basically checked every size. So this one checked all of the hexagons that were bigger than 4. And then we just drew out the 2 case as well as the 3 case.
Yeah, so there's actually lots of ways of doing this question as well, but like, can you see having this expression? So if you look at the expression for inside, if you look at the expression for inside and the expression for outside, so if you move a bit to the left, so having this expression allowed us to make a lot of conclusions. And so the argument we had, maybe you would like, it was based on sort of the kid's suggestion that it should be bigger, right? So the one thing that you might think might not be very nice about it is that we have to think of 2 different cases, so when it's bigger than 3 and when it's not bigger than 3, right? You can think of that there could be actually an argument that gets both cases in one go, but maybe slightly I don't know, beyond your level at the moment, but basically, can you see that the outside is always a multiple of 6? Okay. And the inside, well, everything's a multiple of 6 except for the 1 at the start. Okay. So we'll learn, hopefully, eventually that, well, I mean, you should probably have a good idea of this, but something that's a multiple of 6 can never equal something that's one more than a multiple of 6. Okay. So being a multiple of 6 means it's on the 6 times tables. Whereas, if you start skip counting at 0, skipping by 6, you'll eventually get to all of these multiple of 6. But if you start at 1, you'll get to all these different numbers, right? So
this
something
is
which has no remainder when you divide by 6, or it's a multiple of 6, cannot be the same as anything that has a remainder of 1 when you divide by 6. That makes sense. Have people done remainders?
Yep, I did that. You can just basically.
So Lewis, does that make sense?
So the remainder is basically unique. It can't change from 1 to 0 like that. So
yeah, so this number here, the outside counting, gives us remainder 0 because it's on the times table. So this one has remainder 0, but this one is stuff that is on the 6 times tables, and then you add 1. So by adding 1, we get a remainder of 1, which is why the remainder 0 number and the remainder 1 number are never equal to each other.
yeah, like when you have a multiple of 6, you can share it evenly between 6 people. And this one, you can't share it evenly between 6 people. So that's a fundamental difference between the two numbers.